Okay, let's get started. So thanks everyone for coming to the IUR seminar. So we're very delighted today to have John Birge. So John earned his bachelor's degree from Princeton and a master's and PhD in operations research from Stanford, working with George Dantzig. So usually we have the seminars in our George Dantzig auditorium, which recently opened a few years ago, but unfortunately now no one is actually physically there. But I thought I would just mention that. So John is currently a professor of operations management at Chicago Booth. He studies broadly mathematical modeling of systems under uncertainty, especially for maximizing operational and financial goals, using methodologies of stochastic programming and large-scale optimization. He's also done work in the energy sector, where his interest has been on mechanisms for including uncertainty into unit commitment and capacity investment problems. He's won several awards, including being a fellow of Informs, the IIE Medallion Award, and he's also a member of the National Academy of Engineering. He was previously the Dean of the McCormick School of Engineering and Applied Sciences at Northwestern, and he's done consulting for various different companies. So without further ado, please join me in welcoming John Birge to give today's seminar.
Great, thanks, Paul. Let me find my screen. All right. Okay, let's see. Okay. Yeah, so hopefully you can see that. And yeah, so as Paul said, I'll be talking about price integration in commodity networks. First, I just want to say thank you for inviting me. I'm sorry I'm not speaking in the Dantzig lecture hall. And hopefully someday I'll get to see it if we're ever able to go back and be human again. But this is work that I've done with a number of co-authors, particularly Tim Chan and Ian Zhu at U Toronto, and former postdoc of mine, Mike Pavlin, who's at Wilfrid Laurier University. This began with some work that Mike and I did on electric power networks, and then we thought, well, let's look at some different kinds of networks. And the thing that sort of binds them together is that we can discover properties of the network from information that we observe, and how we observe that information is looking at the solution, what basically the market has provided as a solution to an optimization model, and then trying to use that solution to obtain what the parameters were for that optimization model, and that's what we're trying to understand here. So that's kind of the big picture idea of this. So I'll talk a little bit about networks. So networks, of course, are all over, kind of universally affecting us in different ways, and they represent different things, you know, social, biological, physical, and financial. You can put in there as well. But we often don't see the network structure directly. So a lot of this is about trying to identify what that network structure is. And it may not be completely obvious. So that's kind of why we want to be able to discover what it is. And that the actions that, in particular, when we look in markets, The actions that agents take, people, firms, even perhaps governments, all those actions imply something about what the agents are doing, that they're trying to achieve some objective. So some kind of optimization, I'm assuming, is underlying what they're doing. And that by observing things like what prices there are in these markets, we can recover some kinds of information about them. So using those observations about, let's say, prices, in order to uncover what the underlying structure of the network is. And that's kind of what this is aimed toward. So what I'll do is I'll talk a little bit about networks, and then this general overview of discovering what's going on in these networks. And then the focus will be this example for the US gasoline network. And what I think is interesting about it is that some of it is revealed. That is, we know basically where the pipelines are in the US gasoline network. But that's only one of the modes of transporting gasoline from one place to another. Much of it goes on trucks. Much of it goes by sea. So it may even go by rail. So it may go by any of these different modes, but we don't necessarily see all of the resources that are necessary to transport gasoline from one place to another, or to absorb gasoline into one place relative to another. So we'll look at it in terms of this underlying optimization model, and then talk about what kind of inferences we can draw from that. In particular, what kind of inferences we can draw from the prices that we see, and prices over time. And then I'll talk about some conclusions and extensions of this kind of work. So certainly this is some time ago, Facebook graph of connections. Well, of course, these are sort of virtual connections, but who's friends with whom? Spanning the globe, those social networks certainly are important things to consider. With like social media, biological networks like this graph of molecular interactions in protein, determining what those interactions are, determines what maybe the protein does, or understanding what those interactions are can enable us to determine what the protein does. So those are other ways in which we might look at networks. We're trying to understand what's the structure. We see what the function is. We try to understand what the structure is, and then see, oh, maybe that structure has something to do with what the function might be. And as I said before, I've been interested in electricity networks because they also provide connections. And sometimes the networks are not totally observed. Most of the time, a lot of it is observed. We can see much of the transmission networks that bind generators and loads or demands in these electricity networks. But sometimes they're not. In fact, with the U.S. security laws, that the transmission network is not completely revealed, so it's not totally revealed for as a critical infrastructure for the security of the grid. But what is revealed are prices, and in fact, in many places, prices and quantities. So you can see prices and quantities. From those prices and quantities, actually, you can uncover what the grid is. So we can recover the grid from seeing prices and quantities. So that was work in electricity. But there's a lot of structure we already know. So so the example I'm going to talk about is where there's a lot of structure that's really not known. I don't know exactly how many gasoline tanker trucks there are, and I don't know where they are, and I don't know how many places there are where they could unload their fuel if we even had enough of them. So many of these things are not directly observed, or at least not directly cataloged. And so trying to understand what those capacity constraints are is somewhat more difficult maybe than looking at electricity. So the general process that I'm going to follow is what I've been calling inverse optimization, because that's mostly the way we describe it in optimization circles. But trying to use the solution of an optimization model to identify the structure of these networks. So learning the unknown parameters using an optimization model. Now, most of the time, there are things like I'm interested in learning what it is that people are trying to do. So I'm interested in learning what their objectives are. So I see what choices they make. I see what products they buy. I see how many products they buy. And I might see characteristics of them. And from those observations, I want to infer what it is that they were, what were their goals in making those choices. So that's uncovering an objective function, covering parameters of an objective function. And I would say probably at least in the optimization literature, that's the most common kind of thing that's been done in terms of inverse optimization. What I'm going to focus on is more uncovering what goes on in the constraints. So that's where the structure of the network is inherent, and that's where I'm trying to focus. So I'm trying to look at what is that structure, and how can I use observations about these prices to uncover what that structure is. And as I said, in some of this earlier work with Mike and Ali Hartachu, a colleague of mine at Chicago, we looked at how we could uncover the transmission network of electricity market by observing, in this case, prices over time as well as quantities, the amount that's generated in different places or the amount that's consumed in different places in that network. So generally, this is it's sort of a principled framework that is assuming that there is some optimization problem that's underlying it. It's a framework that can be used whenever I see what the results are of optimization of an optimization model, of the decisions that are inherent in that model. And as long as there is some sort of market that's leading towards something like an equilibrium, the equilibrium you can think of as some kind of optimization, at least the result of maybe multiple optimization models coming together and giving a solution. So that's kind of the overall framework of how we're going to approach this problem. So in looking at this, and this is sort of a key concern in the electricity industry, it's a key concern for determining market power, for knowing whether a particular generator has power over prices, can sort of set prices in a given region. In order to be able to do that, I need to know how isolated that generator is in the network, or how integrated that generator might be in the network. So what we are trying to do in general is to see how well integrated is the network. That is, how much in terms of a barrier does the network, the structure of the network, how much does that prevent, let's say, flow of goods from one place to another? So if it has some sort of capacity, how much does that affect the flow of a good from one location to another location? So that's this overall network structure that we're trying to understand. We can think of it as determining how well things are integrated. Now, statistically, this relates to this concept of co-integration, that if I look in two different places and I see prices that are similar, then I would say that those prices are co-integrated. Now, if they're similar most of the time, those tests often will say those prices are co-integrated, even though there may be certain times when those prices deviate. Now, I'll show you an example in a minute. So in general, these tests of co-integration, which you can think of as kind of a generalization of correlation, these tests of co-integration don't necessarily reveal that there may be submarkets, there may be pockets that become isolated, but they only become isolated under certain conditions. And those conditions are when, for example, the links of the network are congested, or when the capacity in the flow of goods from one place to another are restricted. So the overall goal of this is to use the fact that we think that network is in equilibrium, and let's say we know, at least over shorter time scales, maybe the structure of the network is not changing. And then what we want to do is to discover those components of the network that are integrated, that is where we basically don't see large deviations in prices, or where prices are essentially highly correlated with one another, and the presence of capacity, some sort of capacity that gets exhausted at certain times. So that's the idea of these capacitated links. Now I'll put that and make that a little bit more clear in the next slide here. So the standard test for co-integration is what I show here, that generally it's that, let's say I'm trying to measure something in one place at a given time. Let's say this is a price lambda here. So here's this price lambda in location I at a given time t. I say that it's co-integrated with the price at another location if I can write it as some sort of linear function or affine function of that other price. And then anything that's left over, the residual, is essentially the same over time. So as long as that residual is stationary, so I do, in other words, I do a regression on, let's say, the price at place I on so my independent variable would be the price at place J, dependent variable being the price at place I. And I do a regression on that, and I look at the residuals, and I test the residuals for stationarity. And if the residuals pass this test for stationarity, then I say, oh, these two prices are co-integrated. And often that will say, oh, prices are co-integrated. This is the difference between prices. This is the difference of the price in Alabama relative to California, the average gasoline price in Alabama relative to California, the average gasoline price per gallon these are cents per gallon, in Alabama versus Florida or Illinois or New York. So you can see, okay, Alabama on average has lower prices. And you might think, okay, so Alabama's prices are co-integrated with those in these different locations. So often these tests will reveal that yes, Alabama's gasoline prices are co-integrated. That is mostly the residuals after forming a linear regression. Those residuals end up being stationary, or at least passing tests for stationarity. But what we'll see is that there are often significant deviations. So I'm showing on this bottom chart, these are prices in 3 different locations: Memphis, Baton Rouge here in red, and New Orleans in blue. And you see, as you see, most of the time, these prices follow the same sort of trend. That is, Memphis appears to be a little bit more, a little bit higher than the towns in Louisiana that are closer to the coastline. And that seems to happen most of the time. But then there are certain places where there is significant deviation. So we'll see, like here, significant deviation in the price at Memphis. Or here again, a significant deviation in the price in Memphis, or up here again, a deviation in those prices. So what this work is about is trying to understand when do these deviations happen and what's causing them, and how might we be able to say what cities are going to be grouped together, what are actually co-integrated sort of substantially, and which ones have some sort of departure. And that indicates that there is some kind of congestion, some sort of capacity issue that's preventing flow, for example, from Louisiana to Memphis. Okay, so that's where we're going to be going. Now I'll start to talk about the model that we're going to use. Before I show the model, just to go over the notation, which I don't expect you to remember, but basically there's a set of nodes. There's some consumers and some producers. And there's a set of edges or links. And there are paths. So I'm going to talk a little bit about these paths. How many paths that can go from one location to another. So to go from I to J. I'm going to measure welfare for the consumers, cost for the producers, incoming and outgoing nodes. And this PQ is going to be, this is the cost to go along a particular path from one location to another. And then each of the links is going to have a cost associated with it, as well as a capacity. Again, I'm not necessarily going to know what that capacity is, but they have some capacity. Then there's going to be some flow along these things. Okay, so the first thing I'm going to assume is that this is a fairly competitive market. That is, we're somewhat close to some kind of social welfare maximizing, net social welfare maximizing allocations, and but subject to the constraints of the network. So it's maximizing the net surplus, the net difference between the consumer's welfare and the costs, with whatever the flows are across this network, as well as whatever is being produced and whatever is being consumed. And the flow is restricted to be less than or equal to these capacity constraints, and everything that's produced and consumed is not negative. Okay, so from that optimization model, we can look at the equilibrium, or here optimality conditions, that it would infer, or what it would imply. And we could write those down like this. So there would be some costs at the sources, some costs to consumers. I can describe the difference between prices at two different places in terms of costs, and then some multiplier that's associated with either not being able to go below zero or meeting the capacity constraint. So it's these differences between those prices that I'm particularly going to use, and then the fact that these multipliers only apply if I'm at the limits. And so yeah, so we're going to use these optimality conditions to try to discover what's going on in these networks. Okay, so this is talking about those optimality conditions. So another way I can rewrite them is to say, if I take any two nodes, then the difference in the prices at those two nodes can be rearranged to be written as the price along some path, price of all the costs along that path, minus, let's say, the multipliers that are associated with the flows that are at their bounds. This would be, I guess these were the flows that are at zero, and these are the flows that are at their upper bounds. That gives us some additional conditions on what the difference in these prices might be, which I could otherwise state as, if there's a positive flow that's going from node here, node N1 to node N2, it's the physical cost plus the cost of being at capacity. So we have sort of the physical costs plus these capacity costs along the path that goes between those two nodes. And that means that I can look for prices at different locations in terms of, well, what's the cheapest way that I would go from a given location to that other location, assuming that I also absorb these capacity costs. Now, with this gives us a way to talk about when a network is integrated and when it is not. So we say that it's structurally integrated. That is, that I can get flow from one place to another. If the set of consumers that I can reach from one location and another location is the same for all locations that are in this set of nodes. So think of these as my sources, my locations of, let's say, gasoline producers. And if I can get to the same set of customers from those gasoline producers, then I would say that the set of nodes is structurally integrated. That effectively means that this market is structurally integrated if there's any path that goes between any two nodes. So as long as I can get between those two nodes, if there's no constraint in the capacity, then they'll all have the same price. So if there's no transportation cost and no capacity, or all the capacities are infinite, as long as they're connected, there's some way to go between two of them, then the price of commodity is the same everywhere. So this is just saying there's another way. When I have costs in going from one place to another, we say that the pair of nodes is structurally integrated. In other words, that the two of them can be mutually are mutually accessible, if and only if the price difference is bounded by the difference in the cost. So whatever the difference is in the cost of transportation between those two locations, that's going to bound the difference between those two prices. So if there's no capacity constraints, then prices should always be within whatever the differences are in terms of the costs of moving the commodity from its source to one of these destinations. Now, the congestion surcharge is what applies when there is a capacity, finite capacity, and when the flows might reach that finite capacity, and therefore that one of those multipliers in that optimization model would then be positive. In that case, that means that the price difference is not just between, let's say, these two locations. The price difference between those two locations is not just, let's say, the difference in the transportation costs to get to those two locations from a source, but it may also include any capacity constraints along the way, any congestion charges associated with moving the commodity from the source to one of those two locations. So so we can say that the difference in these two prices is normally bound by, let's say, the difference in terms of transportation costs. If one place is more expensive to get to from another, then it would have the higher price, but will be limited by whatever that transportation cost is. And then in case there is an additional capacity constraint that is binding, then we would include the surcharge for that capacity constraint as well. So here's little examples to see the effect of this. So I've drawn a network here where here are my sources. So the producers are down here. They have to go through this node, S1, in order to reach customers at S2 and S3. And this link only has capacity of 1. So that's all they can get through to S2 and S3. So S2 and S3 combined can only absorb this 1 unit of capacity. That means the price is quite high in those two locations. S1 is able to get any additional capacity from here. So the price, basically, price in these S2 and S3 is going to be the same. as each other, but it's higher because of this capacity constraint. If I add in a link that goes from S1 directly to S3, now I've sort of separated S2. So S2 now is in a different situation. It's no longer totally integrated with S3. So S2 now can get this 1 unit, but S3 can also get 1 unit. So we then have a solution here in which prices everywhere have gone up, well, everywhere except everywhere in this bottom part have gone up. But I'm able to get this 1 unit going up to S3, and you know, we get 2 different prices in those locations. Now I could also have a situation where, let's say I added a node, or I added a link that went from node K1 directly up to S3. In that case, now I'm able to transport this 1 unit directly up to S3. Gives me a higher price there, different prices in S1 and K2. These are like the costs if I leave this node out. So if I leave this node out, I don't have really any effect on S3, but I have a huge effect on S2. So the effect of leaving this node out is greater for S2. That should be or the maximum value, which would go through S2, greater for the maximum going through X2 than it is for going directly to S3. So seeing these different prices actually gives me information about what the network might look like. So seeing prices like this means that I can infer that this link is there. Seeing prices like this would mean I can infer this, or seeing just these 2 prices the same would mean that I only have this single link that relates these nodes to the others. Okay, so what we'd like to be able to do is to discover where those increases in prices occur, and we'll call those surcharges. So we'd like to discover where those surcharges are, and try to estimate them, seeing a lot of observations. So if I see a lot of observations, then the price that I see at any point in time at any location is going to be some function of what's going on at that given point in time. So some sort of function of, let's say, overall production or overall demand. Something about that particular location, such as the price of transportation to that location. Something about congestion, and then something that's somewhat random. So we would like to be able to identify, well, what's this congestion part? And that will tell us where the congestion might be, and how much is going into the rest of this. And a way to do that is to look at, well, how big might this, what I was calling before the residual term, how big might that residual term be? And I know that it can't be too big if there's no congestion. So I'm going to look and see, well, if I place limits on how large that error might be in this model, I'll place limits on that error, and then whenever let's say the price or the difference in prices are outside of these limits, then I'm going to assume that I have some kind of congestion, and I'll absorb that into W. And that's what this model is doing down here. It's saying, I'm going to limit the amount of what these errors might be, and then put the rest into this W parameter. And that looks like this overall. So if I solve all this together, I solve this, here it's a mixed integer program. Solve this integer program to uncover whether I'm above or below those values, and then set whatever these limits might be, and then use that to uncover what those prices should be. Okay, so I'm going to try to uncover this market price, these transportation costs, they're essentially the location dependent costs. And then this measure of integration, which is what the normal band is, as long as I'm not exceeding whatever the capacity is. So I'm trying to discover what is the sort of normal variation in prices before I start to exceed whatever the capacity is. And then I'm going to also uncover then, given that I have that, I can uncover what these congestion charges are. And the parameter I'm going to use to sort of elicit this is I'm going to exogenously put in how congested, how often the network is congested. So I'll exogenously put in a fraction for the amount of time that the network is congested and that I'm going to observe these congestion surcharges. Now, I'll then actually try to estimate on the basis of how well I fit to the observed data what that congestion charge might be, or what that congestion frequency might be. But for now, I'll assume that this is just given exogenously. Okay, so let's use this case study. So this is southeastern US. Southeastern US because it does show significant variation in prices across time sometimes. And it's also susceptible to both weather as well as other hazards. So I'll look at that. And I'll look at retail gasoline prices across this region for a period of 4 years. And as I said, the prices are going to be quite similar most of the time, but then show some variation. And most of these standard models just will say that their prices are integrated, even though there are these periods when they deviate. And then we'll uncover these critical links. So here are some prices. As you can see, most of the time the prices sort of follow each other, but there are certain times when we see some deviations. So this location, we see significant deviations here. We might see some others up here. So we're going to try to uncover what those periods are, when prices might be deviating, and then try to understand what the capacities are that are limiting that. So as I said, I vary the amount of the overall frequency of surcharges. And here this says surcharges only occur 5% of the time, surcharges occur 50% of the time. And these are the surcharge variables that result from that optimization model when I do that. So it says, well, I have 2 periods where there were these surcharges in different locations. So it looks like in 2 periods, I at least at the beginning, in 2 periods, I see that I hit some sort of congestion. As I increase that frequency, it looks like, well, this is kind of growing this period. And maybe there are a couple of other periods when I might have some observations of congestion. And then when I make it 50%, I get several of these. Okay, so so what has this done? Well, this is effectively identified that if I look at these places, I've labeled them A, B, C, and D, and E here. It looks like in this case, B and C, so B and C are the green and the red. Looks like they separate out here. It looks like A, which is in blue, looks like the blue, which normally is kind of at the bottom, but it looks like it separates out here and again over here. So this would identify that B and C are locations that are often co-integrated with one another, but many, or at times, not integrated with the rest of the market. And then A often, at least in these two times, gets separated from the market. If I do that overall, I see something like this, that in Florida, if I go from Orlando up to, I think, or Tampa, up through Orlando up to Jacksonville, that's integrated. I see some integration between Nashville and Atlanta. And then in these, this sort of western or central part of the Carolinas. But to try to understand it, I'll look at a very specific example. So I'll look at this example here. There's a pipeline disruption. There are two major pipelines that are shown here. Blue one's called the Colonial Pipeline. The red is called the Plantation Pipeline. So there was a major disruption on the Plantation Pipeline in this period in 2016. And what our model identified is that there were significant changes in the prices when that disruption occurred. So the disruptions in this shown here in red. So when that disruption occurred, first prices are not changed too much, but after a few days, effectively storage is exhausted. They're not getting more through the pipeline. So prices start to diverge in, I guess, Georgia and Nashville in particular, Atlanta and Nashville in particular. And prices sort of remain diverged. Now, if it was only the pipeline, then we would expect the same thing to happen here. This is the cumulative amount of the surcharges that are aggregated over the time period that I'm showing here. So we see that there's a significant amount in Atlanta and Nashville over this period, not so much in the Carolinas. Now that's partly because what's happening is the Colonial Pipeline actually bypasses. I don't think it has an outlet at Atlanta. And then the next place I think is in Greenville in North Carolina, or on the border with South Carolina. So there's a large section that's not served by any pipeline. But once I get beyond that, it looks like that these locations actually have significant amounts of other kind of supply. So it identifies that there are other ways in which gasoline is able to get to these locations, but that Atlanta and Nashville in particular are susceptible because they don't have necessarily the capacity that the others have. Here's another example of hurricane. Again, I thought hurricanes would particularly impact Florida. In this case, the impact on Florida was actually not too significant. Even Miami, which Miami has no pipelines, is effectively just served by the port. So gasoline arrives by ship, and for the most part in Miami. After the hurricane passes, even though the ships can't port, after the hurricane passes, the ships can come in, and then the supplies regain. So it appears there's really not as much of concern. There is some, some deviations in these locations in Florida, but much more significantly along that pipeline corridor. Okay, so what this study does, it shows the vulnerability in some of these locations. Miami, even though Miami, from perspective of pipeline, is totally isolated, but it seems to be well integrated just because of its port. And hurricanes, because they don't really last too long, don't have a huge effect on it. Memphis is better integrated than Nashville, and has resilience, probably because of a lot of ground transportation available. But those regions that have just a single pipeline are somewhat limited in their capacity to absorb shocks. So to conclude, incorporating observations can identify some of these hidden network structures. It allows us to study other kinds of things that might happen, like what might happen dynamically if I change conditions. It gives some perspective on policy efforts. There was a discussion about an additional pipeline in Florida. At least from this study, it tends not to support having an additional pipeline, at least that the value would be relatively low. So we can do those kinds of studies as well. I mentioned extensions. We can think about this in different contexts, and getting additional insights from these problem structures. And then looking at things like when should new competitors enter into a market? When should they exit a market? Based on the availability of these capacities, what's the value of adding that capacity, like the value of adding transmission or value of adding a pipeline in this case? So we can answer questions like that and look at what happens when firms enter or exit. And that we can extend these to other kinds of network designs. Okay, so thank you for your attention. I don't know if I have a few minutes for some questions.
Yes, we have a few minutes, so anyone who has questions, feel free.
I'll stop my sharing.
There's a question in the chat.
Okay, let's see. Oh yeah, so the impact of storage. Yeah, so storage, what you can, I didn't model storage explicitly in here, but you could include that as well. If you look at that example I did with the pipeline, there was absolutely no effect for several days. So we think that that's probably because of storage. So you could explicitly put in what's a storage resource, or how much does this location have in terms of storage resources? And by observing how long before the impact of any kind of disruption occurs, you could try to recover what the storage might be. So without having to know exactly what the overall storage might be on the network. Any other questions? Well, thank you. Thanks, everyone. And I hope next time I get to see everyone physically.
Yes. No, thanks so much, John.
Thank you.
Thank you, John.
See you
All
soon.
right.
Yes.
Thanks. Thanks,
Thank you.
everybody.
Thank you.
Thanks. Bye-bye.
Bye.
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 Thank you.
Bye.